Well, hello everyone. My name is Cassie Luna. I'm a biotech engineer and currently a PhD student. So, along with my Team 4, we're gonna be talking about some of the conclusions we made after discussing chapters 1 to 4 and also some key concepts. So, I would like to start stating that as engineers, we are traditionally trained to think and operate in a world of deterministic models. For example, from our earliest courses, we learned that if we apply a force to a mass, the system will respond with a well-defined acceleration. If the equations are correct and the assumptions are satisfied, the results should be exact, unique, and reproducible. This framework is appealing because it is clean, structured, and mathematically elegant. It gives us a sense of control. If we understand the system well enough, then we should be able to predict its behavior precisely. However, this assumption hides a fundamental problem. It does not reflect how real-world systems actually behave. Outside the classroom, engineering systems are saturated with uncertainty. Materials exhibit microscopic imperfections and variability. Sensors may introduce noise, bias, and delays. Environmental conditions change continuously and often unpredictably. More importantly, many real systems are only partially observable, since we simply do not have access to all the variables that influence their behavior at any given moment. Despite this, traditional programming and modeling approaches often force reality into binary categories: true or false, detected or not detected, safe or unsafe. These simplifications are convenient, but they overlook a critical fact. Uncertainty is not a flaw in measurement, it is a consequence of incomplete information. This realization began to take a more formal shape in the late 1980s, particularly through the work of Edwin T. James and his formulation of probability as logic. James argued that probability should not be viewed merely as a statistical tool, but as a generalization of classical logic, one that allows us to reason consistently when our knowledge of a system is incomplete. From this perspective, uncertainty is not something to be eliminated, but something to be reasoned about. We do not lack rigor because we are uncertain. We are uncertain because the world does not reveal all of its states to us. Many of the variables that affect the system behavior are hidden, unmeasurable, or only indirectly observable. The core challenge, therefore, is not randomness itself, but incompleteness. Building on this foundation, Bayesian programming emerged as a formal framework for engineering under uncertainty. Instead of representing variables as fixed, exact values, Bayesian methods model them as probability distributions. For example, we no longer say that a temperature is exactly 20 degrees. We say that it is highly probable to lie between 19 and 21 degrees, with decreasing probability outside of that range. In doing so, we explicitly encode both that we know and what we do not know. This approach proved particularly powerful in fields such as robotics and autonomous systems. The work of Olivier Levitin, for example, demonstrated how Bayesian interference could be used to address localization and navigation problems in environments where key state variables are hidden. His contributions show that many failures in intelligent systems were not due to poor models, but to the inability to account for hidden variables and ambiguous sensory data. By explicitly modeling these hidden states, Bayesian systems are able to maintain multiple hypotheses simultaneously and update them as new evidence becomes available. Rather than committing prematurely to a single interpretation of the world, the system continuously revises its beliefs in light of incoming data. In this sense, Bayesian programming does not attempt to impose certainty where none exists. Instead, it provides a mathematically rigorous framework for managing uncertainty as an intrinsic property of complex systems. It does not replace classical engineering methods, but it extends them by formally integrating uncertainty into the process. However, acknowledging uncertainty is only the first step. For a system to be truly adaptive, it must also have a principled way to update its beliefs when new information arrives. If probability is an extension of logic, then we need a rule that tells us how to move from prior knowledge to updated knowledge, without inconsistency. That rule is the Bayes theorem. So in the next blog, one of my teammates will go more in depth with the technical aspect of it.
Hello everyone, I'm Antonio. I'm a mechatronics engineer and currently a student in robotics and control. I want us to take us into the technical core of the book, the actually machinery of Bayesian programming. So in classical control theory, which is what I usually work with, we're often obsessed with modeling the system perfectly as it is. We want precise differential equations to predict exactly how the robot moves. On the other hand, the others argue that we cannot model everything perfectly, so they define Bayesian programming, which is formally two parts: a description of the world and a question we ask that description. So let's break down the description. In my field, we would call the description a system model, but here it is built into two rigorous phases: specification and identification. So let me break this down to you using the Kepler robot example. So in the phase 1, we have the specification. The specification. This is what allows us to structure our knowledge before we even touch the data. It consists in basically 3 steps. We choose the variables. We don't track every single little variable. We select by relevance. For example, in this case, is the direction of the obstacles, the proximity, and the motor rotation. Second is the definition of the decomposition. This is fascination for us control engineers. We take the complex joint probability distribution of all these 3 variables and break it down mathematically into simpler products. This is where I, as an engineer, inject my subjective knowledge, and I assume, for example, that the sensor reading depends on the object distance, but the object distance does not depend on the sensor. And finally, the third is we choose the parametric forms. We assign mathematical shapes like bell curves or Gaussian curves to these relations. At this stage, it is crucial to understand that these curves are empty, and we have to fill those curves with information. So for phase 2, which is identification, basically learning from the data, the algorithm takes this raw data and shapes the empty bell curves that we defined earlier. Here is where this Bayesian programming is really impressive. For example, the impact on robotics is huge. The book demonstrates that by using the exact same code, but simply changing the training data, the robot can learn 2 completely different behaviors. For example, if I train it by pushing boxes, it learns to be aggressive. Meanwhile, if I train it to follow walls, it becomes kind of a path follower. So basically, this means that we are not coding if-then rules like normally. We are training like the probability distribution of this robot. So finally, once the model is trained, how does it make a decision in real time? This is the question phase or inference phase. In a standard PID controller, I calculate an error and the system outputs a specific voltage. In Bayesian program, I ask a formal probabilistic question. Given the values I see on my sensor right now, which is the known part, what is the probability distribution of the motor rotation, the search part? The robot doesn't output a single certainty. It calculates like the probability for every rotation speed. It then draws a value from that distribution to act. So finally, to conclude on the impact in my field, chapter 3 explains that all models suffer from incompletenesses, which is hidden variables like friction, battery level, or wheel slippage that we cannot control and we cannot ignore. Usually, in robotics, we treat these annoying errors as noise, but Bayesian programming transfers this incompleteness into uncertainty. So by quantifying what we don't know, we can build robots that are really efficient at and can navigate safely in the real world, rather than crashing because you didn't take into consideration one or other variable.
Hi, my name is Carlos Armando Figueroa Perez, and as engineers, a mechatronic engineer, we're taught to simply model systems with measurable variables and to treat everything else as negligible. But what if those negligible factors aren't so negligible after all? In Bayesian programming, we start from a subjectivist premise. Every model of a real phenomenon is incomplete. There are always hidden variables, factors we didn't measure, didn't consider, or simply we didn't know that they existed. And this isn't a flaw on how we approach reality, but it's just reality itself. It forces us to ask, when do we need to move from a deterministic model to a probabilistic one? As chapter 1 says, a good model should take into consideration its own incompleteness and the resulting uncertainty for it to be truly useful. So, when do we know how to consider or not consider these variables? Where the answer lies in experimentation and prior knowledge. Through hypothesis testing and data, we can detect whether unknown variables are affecting our outcome, and if they are, Bayesian programming gives us the tools to quantify their influence, even if they remain hidden. Just like the steps to develop a Bayesian program, we have to create a specification, therefore an identification, to then the description, to later a question. To develop or to get to know this experimentation prior knowledge about these variables, we're talking about an identification step. We're using data to transform an incomplete specification into a probabilistic description that captures uncertainty. For example, if we're talking about my field of specification, we're going to talk about soft robotics. We're going to use an example like the curing process of a given robot that we're manufacturing using a casting method. We're going to provide a comparison, just like the water treatment system provided on chapter 3. We have the variable Ft, which is the furnace temperature in which is curing the robot, the elastomer consistency, the TC curing time that we're giving it inside of the furnace, and as an output, the P performance in terms of elongation compared to what a theoretical value of this elastomer gives. But we also have, just like the water treatment, a variable R curing rate, which would be similar to that of the F variable. We cannot measure it directly, but a sensor, which is the internal temperature of the mold of that elastomer inside of it, is measured. And we're going to have a Z hidden variable that accounts for the contamination of that elastomer mixture, which would account for different contaminations, just like dust in the ambient, humidity, and some debris that might have been left off when mixing the compounds. So just like the water treatment system, if we were able to conduct an experiment instead of a simulation, we would observe that some batches of those robots of the manufacturing method would have different performances between them, even though we would be able to make them the exact same way in the exact same conditions. This would be because of a not consideration of a set variable, C variable. So if we ignore C, we would be clueless about what would be the effects, the causes of this malfunction. But through Bayesian identification, collecting data from multiple runs, we can infer the effect of C on R and thus on the performance P. With this, we're not just detecting noise, we are learning the structure of our ignorance, and that allows us to make better decisions, like tightening environmental controls or adjusting curing parameters to reduce variability. Soft robotics, where material behavior is highly sensitive to fabrication conditions, this isn't just theoretical, it's practical. Whether it's curing, molding, or in actuation, hidden variables affect reproducibility, safety, and therefore performance. So, where do we draw the line? When our models start failing in unpredictable ways, when uncertainty isn't just noise but a signal of something missing. That's when we move from deterministic to probabilistic. That's when we embrace Bayesian programming.
Hi, my name is Ricardo Navarro, and well, we already have discussed what is the Bayesian programming and some examples, but I want to recap a little bit in this in particular, the examples, because we have now a big question. Where do we use the Bayesian programming? Even though we have already discussed some examples, with the book we saw that there are not only in theory, not only in equations on a board, but in a frontier engineering system that must act under uncertainty, incomplete data, and constant change. That are the particularities that we have this type of programming. Because as I already said, this is exactly what Bayesian programming was designed for. With the book, we have already accept the idea, or the idea becomes clear that instead of trying to eliminate the uncertainty, we model it. So with that, we can explicitly define variables, assign probability distributions, and describe the causal relationship between them. So we stop pretending that the world is deterministic, and we start programming reality as it truly is, as stochastic. As I already said, we have already explained some examples, but a more commercial or breakthrough ones nowadays are, first of all, in the field of robotics, we have the rover on Mars. This type of robots, because we know there is an environment, a really noisy environment that will affect all of our sensors. And a part of that, the transmission time between Earth, Mars, Earth, it's really long time. So by the time some situation occurs to the rover, it will be already really late to make some type of change, or even make a real-time change or interpretation of the data that the robot is having. So with that, we can already see a really good example of how the Bayesian programming here is essential, because instead of having all assumptions that what has to be and what to do in each case, we have now probabilities of what is going to pass. So if we have some data from our sensors, the rover is going to know what to do. Instead of what is the exact state I am, it will be the question will be reformulated to what is most likely given the evidence I have. This will give the rover a possibility to survive in the chaos that will be in this environment in a specific, because it has a lot of data that we don't know, and the rover must do some elections in that moment. In the other hand, we have the field of civil engineering with the digital twins. This is a replica of, how we see some of the structures that are in the construction sites. And we can create these replicas knowing some of the factors that will be affecting. We may not know all of them, but we can make a great probability of what is going to happen to all of them, taking on account the factors that we already know, and to make simulations of them. As I already know, it's really simple. Everywhere it's a good way or a good start point to use the Bayesian models and the Bayesian programming, mainly if we know that we have a changing environment constantly. So really, even though we more new example, we want to introduce this concept of computational intuition. We know that the Bayesian programming will have not to be seen as a technique. It's more like a way of thinking. It forces us to ask, what do we know, what do we don't know, and how confident are we? So we have like for years trying to achieve an absolute precision in engineering, and with these Bayesian models we want to bring back this idea of computational intuition. Nowadays we are teaching machines to reason like humans with the AI, so to form hypotheses, updating beliefs, but at the scale of millions of data points per second, the gate is absolutely this Bayesian programming. The future of engineering is not about removing the doubt, it's about programming with doubt and turning uncertainty into the intelligence. Thank you.